Okay, hello everyone. So today we're going to be talking about sections 2.5 all the way to 2.7 and 2.8. These are talking about very important descriptive statistics, the measures of central tendency, the measure of center of the data. We're going to talk about four of those. The first one is the mean, and that's the arithmetic average. You add them all up, and then you subtract, and then you divide by the total number of samples in the size. The next one is the median. The mean is denoted by x bar, which we read x bar or x or mu. The median is the second one, and what that is that's the middle of it. So this is associated with the 50th percentile, P50. So then we have the mode. So we know how to compute P50. Then we have the mode. And the mode is the most frequently occurring of the data. And then there's the mid-range. And what the mid-range, you add the min and the max and divide by 2. And whatever that is, that gives you the mid-range. Now rounding, you always just, so we've talked about this a little bit before, the rounding procedure is going to be one more than where the data is rounded. So one more than data, with the exception of the mode. The mode does not need to be rounded because it is one of the data sets, one of the data values. Let's take an example here. So the mean, x bar, if I wanted to do x bar, I'm going to add up all of my data and divide by n, which is the total number of data. This here is a sigma. If I drew it more neatly, it would look like that. And that's a capital sigma, and it means sum. So I would add all this up, divide by 1 over n, which is, in this case, n is 20. So that would be 66 plus 66 plus 67 plus 67 plus 68 plus ... all the way to plus 73 plus 74. And if I do all that, I end up getting 1390, if I'm not mistaken, over 20, which equals 69.5. So that right there is my mean. Now notice I rounded it to 0.5, and what's the unit on that? That is going to be years. If I add up years, I get years. If I divide by some unitless number like 20, then I still get years. So the unit on this is years. Okay, now the median, which is sometimes indicated by x tilde, is just going to be the center of the data, the middle of the data. And so I've got 20 data points, and so I'm going to take the two middle points, which is this one and this one. There's 9 on that side, 9 on this side, and 9 on this side, 9 on the other side. And I'm going to average those 2 points. 69 plus 69 over 2 equals 69 years again. Now, technically speaking, I really ought to put 69.0 because that indicates that I've rounded to one more than the data. So 69.0. That 0.0 is not all that important really though. But to be technical, I would add that. The next thing we want to do is find the mode. So the mode is the number that occurs the most. So let's just take a look. What would that be? Well, I think it's going to be 68. Let's see. 1, 2, 3, 4, 5. Are there any values that appear more than 5 times? The answer is no. So we've got 68 is the mode. Now there could be more than one. And you've got to be careful because Excel will only give you one. that might not be the right answer. There might be more modes than that. So Excel might give you the wrong answer if it only gives you one mode. Okay, now the mid-range is going to equal the minimum plus the maximum over 2. I average those. And I end up getting 140 over 2, which equals 70. So that's my mode, my mid-range, 70 years. And again, I could put 70.7, 70.0, or 68.0 is not necessary. But this is still years. Okay, so there's the example. Right, remember, this one here is min, this one here is max. That's the mid-range. Okay, mean using a frequency table. Use the same boy's height as the data above, these 20 sets, and then make a frequency table. All right, so here I go. So 66. So I've got 66, 67, 68, is 60, 69, 70, 71, 72, 69, 70, 71, 72, and then there's 73 and 74, 73, 74. Now, sometimes you are given a frequency table because the data is, there's lots and lots of data. Sometimes it's a lot more economic to put it as a frequency table. There are 2 66s, 2 67s, 5 68s, 3 69s, 170, 171, and 72. How many 72s? There are 3, 2, and 1. So 3, 2, 1. Let me just check. If I add those up, I get 20. Okay, so if I had a frequency table, how could I find the mean height? And so the way I would do that is x hat equals, well, I know that 66 appears twice. So rather than adding it, 66 plus 66, I could just multiply it by its frequency. Plus 67 appears twice, so I could do that. 65 appears 5 times, so I'm going to multiply that one by 5. 69 appears 3 times, and so on. And then I divide by the total, which is 20. And so that will end up giving me, if I put that in my calculator, it'll give me the same thing. 1390 over 20 equals 69.5. Now the median is a little trickier to find. I need to find so remember, the median is the 50th percentile, and I had 20 data points, so 20 plus 1. So that gives me 10.5. So I need to find the 10th and the 11th data value. Okay, so where does that take me? So here's 2 data points, here's 2 more, so that's 4. Here's 5, so there's 9 data points above that. And then so 10, 11, so 10, 11, and 12, my 10th, 11th, and 12th data point are 69. So both of these are going to be 69. I average those, and I end up getting 69. So that's my median. This is years again. Years. Mode is very easy to find on a frequency table. You just count which one appears the most. That'll be this one. Okay. All right. We can get the exact mean. We can't get the exact mean of the data from a grouped frequency table. So this is a grouped. There's lots of different. This is more like a histogram. So I've got these groups and the frequency of numbers that are within the group. That's a grouped frequency table. But we can estimate the mean by using the midpoint of each class in place of each data value in that class. Okay, so for instance, this is my grouped frequency table. And it probably came about from data like this. So one person said 1 hour, another person said 2, and maybe another person said 1.5, for instance. All of those are between 0 and 3. And so they go into this bin, and there's 3 of them. So then 7 people gave various numbers of hours, and they all fell within this range. And then 12 people gave numbers of hours that fell within that range. We don't have the actual data for all of those. How much would that be? That would be 12, 30, let's see, 29, 38. So there's 38 values that we don't know, but we do know what bins they are in. And so what we'll do is we're going to find the midpoint for each one of those bins, and we're going to use that midpoint to approximate every data point in that bin. So the midpoint for 0 to 3 is 1.5. 4 to 7, the midpoint is 5.5, right? I add those together, I get 11, half of that. 8, 11, the midpoint is, the midpoint is 9.5. 12 to 15, the midpoint there is 13.5. And 16 to 19, the midpoint for that one is, I add those together, I get 35. Half of 35 is 17.5. Okay, great. And so then what I do is I add, so x bar is approximately 1 over 38, because that's the total, times 1.5, times 3 times 1.5, because there's 3 in the bin where the average value is 1.5, plus 7 in the bin of 5.5, plus 12 in the bin whose average value is 9.5, plus 7, 13.5, plus 9, 17.5. All right, and so if I get my calculator, I can add that all up. Okay, I think that's good. Yeah, let me just look over it. All right, and so that's 409 divided by 38 is 10.76. So this right here equals 409 over 38, which is approximately 10 point. Now where am I going to round it? well, I'm not exactly sure. I don't know where the what the data was. I guess rounding to the nearest hour. We'll go ahead and say 7.8. So I had 7.6315, and so I'm going to round it to 17.8. I'm going to assume that they just gave you the number of hours as an integer. And so I round it one more than that. And this is going to be hours, probably hours per day. Hours spent on video games. Maybe, no, it must be per week, right? Maybe hours per week. Hours per week. Okay. Great. All right, so, what now? Yeah, okay, so there it is. So find the midpoint of each class. What is the best estimate of the mean number of hours spent playing video games? So there it is, 10.8. Okay, now the law of large numbers says that as a sample size increases, the sample mean, x bar, that's what we found here, x bar, the sample mean is going to get closer and closer to mu, the mean. So this is our population mean. This is usually what we want to know but can never figure out unless we take a census. And so it's nice to know that there's at least something we can do. We can increase the sample size, or at least something we can do to try and get what the actual mean is. Okay, skewness and resistance of the mean, median, mode, and mid-range. A statistic is said to be resistant or robust if it is not affected by outliers. Not affected by outliers. It resists outliers. Okay, so the mean uses each data point. It uses its value. And so, as a result, if one value is quite large, then it is going to affect the mean. So this is highly affected by outliers. That's the mean. So it is not resistant. But the median, though, as we talked about, it's not affected as much by extremes. It doesn't matter if, so here's my data, like that, and then there's some median. Now, if this one here turned out to be way over here, extreme, the median doesn't change because it's only concerned about how many. It doesn't matter how far out it is. So the median is so doesn't use value of each point. This one is resistant. Is resistant to outliers. It's not going to change if there's big outliers. Okay, the mode is also resistant because the outliers are hardly ever going to be the most common data point. And then the mid-range is definitely not resistant. This one here is also highly affected. And try and think about why that is. Why would that be affected by outliers? Because you have, you use the max and min value. And if there's going to be outliers, they're going to be either the max or the min. So that's why that one is not resistant. Skewness. Skewness is related to resistance. So data is skewed to the left or to the right if there's a tail of the data to the left okay, so it's skewed to the left if there's a tail on the data, to the left of the histogram. So you think about the histogram. Something like this. And if there is a tail, something like that, this is skewed to the right. And as a result, the mean, your mean is going to be pushed this way because these here are going to affect the mean. The median, though, will stay right here. So if there's a tail on the right, follows this sort of, if the tail is on the right, then the mean will be pushed to the right. If the tail is on the left, then the mean will be pushed left, pushed down. X bar. And X tilde will still be right in the middle. That's the median. Okay. All right. Let's see. The mean will be pulled in the direction of the skewing due to extreme data values, due to its lack of resistance. If there are more than, if there's a more mild skew, the median is more appropriate. If there is more than mild skewing, if it's highly skewed, then a median is going to be a more appropriate measure of the center than the mean for a more accurate summary of the bulk data. Okay, and that concludes section 2.5 and 2.6. Now what I want to talk about are measures of spread of the data. All right, so we're going to talk about at least 3 ways of measuring the spread. Okay, so 1, 3, or 4. Okay, so one way of measuring the spread is just the range of the data. And as you can see here, it's going to be the max value minus the min value, and that's the range. So the mid-range gave you what was in the middle of that. This gives you the distance between them. This gives you an idea of the total spread of the data. Okay, is the range resistant? What do you guys think? No, depends on max. Well, okay, it depends on possible outliers. Another measure of spread is the IQR. See, that's a measure of spread. Is the IQR resistant? Yes. Yes, it is resistant because the outliers will not be close to the quartiles. Outliers far from quartiles, which are used to find the IQR. So this is a resistant measure of spread. Variance. Variance is another measure of spread. Variance is the average of the squares of the deviations from the mean. Okay, see, so here's our data. X represents a particular data point. And we sum all of those data points together. So this right here is going to be, okay, and so what you do is you take the square of each deviation. Okay, so here's one data point. Here's my mean, x hat. And here's another data point. So here's x1, here's x2, here's x3. You take the distance between them. So that distance right there, you take the distance between it, and you square it. And you take the average of all of those. And that gives you the variance. The standard deviation is the square root of the variance. So then this is the most commonly used measure of spread of the data. The standard deviation tells us approximately how far data values are from the mean. See, so this thing here is the average deviation when I take the average squared deviation, see, that's the squared deviation. When I take the square root, I sort of get rid of I take care of the squares of the distance, or the squared deviation, and I get instead average deviation. All right, great. Okay, so the idea is that a large standard deviation indicates that the data values are further from the mean on average. Okay, so remember that standard deviation is basically the average deviation of the points from the mean. All right, are the variants in standard deviation resistant? The answer here is no, they are not. They use every value. They use every value. Okay. Interpreting standard deviation. Let's look at this example. Suppose the mean wait time in line at a Publix and BI-LO is 5 minutes. So the mean is 5 minutes for each of those. However, the standard deviation of the waiting time at Publix is 1 minute, and the standard deviation of the waiting time in BI-LO is 3 minutes. Which supermarket has more variation in waiting times? Well, it must be BI-LO, because the average distance of each wait time from the mean, which is 5 minutes, is 3. On average, that distance is 3. So, okay, so here's the mean. Here's 5 minutes. And there's 5 minutes. Here's 6 minutes. Here's 4 minutes. And then here's 8 minutes. And here's 2 minutes. And so, on average, the BI-LO wait times are 3 minutes from the mean. So, and that's an average. So sometimes it's closer, sometimes it's further away. But the average is around 3 from the mean. So that's spread out quite a bit more than the Publix, which has an average that's only, on average, the deviations are only 1 away from the mean. So that's much tighter, more tightly packed. Which supermarket would you, at which supermarket would you be able to predict your wait time more precisely? Yes, very good, very good. Well, that would be by Publix. And that's because the variation is less. 5 is a better approximation most of the time in Publix than it would be for BI-LO. All right, there's a range rule of thumb, and the range rule of thumb is that the range of the data states states that most data is within 4 standard deviations. And so usually in the middle of those standard deviations is the mean. And so it's within 4 standard deviations. However long a standard deviation is, 4 of those will have most of the data. And so, but the total range of the data is the range. And so what that tells us is that the range is about 4 standard deviations, or S equals, so one way to approximate the standard deviation is to take the range and divide it by 4. All right, so the standard deviation can be used to determine if a data value is close to or far away from the mean relative to the rest of the data. So we want to see standard deviation can be used to determine. As a rule of thumb, more than 2 standard deviations from the mean is considered unusual. So if it's more than 2 standard deviations from the mean, it's unusual. Okay. The standard deviation formulas are found okay, so they're a bit much to calculate, even though we saw it already. So, but generally speaking, we were going to use Excel to find the standard deviation. The formulas for the sample and the population standard deviation are different, so that's important to note. The standard deviation of a sample is not the same formula as the standard deviation of the population. By the way, the population standard deviation is denoted by a Greek letter again, sigma. So the deviation of a data value from the mean is the signed distance. So we've got distance. If it's on the left of the mean, it's going to be negative. If it's on the right of the mean, it's going to be positive. And so that's the deviation. The z-score of a data value is the number of standard deviations from the mean that data value is. Okay, so if the data value is below the mean, then the z-score is negative because the deviation is negative. If the data value is above, then the z-score is positive. Okay, so here it is. So the z-score of a point is going to be the deviation of that point divided by the deviation of that set, of the data set. In notation, it looks like that. All right, write the formula for the population z-score using appropriate population symbols. Well, in exactly the same way that it is there, you have z is going to equal x minus mu over sigma for the exact same reason as what we had above. All right, the z-score. Use data for boys' heights, which has a mean of 69.5. We saw that, but there's a standard deviation of 2.5. Find the z-score of a height of 74 inches. Okay, well, so we're going to do 74 minus 69.5, which is going to give us, and then we're going to divide by 2.5. And so this is going to be, what is this, 4.5 divided by 2.5. 4.5 divided by 2.5 gives me 1.8. 1.8. So 74 in the units of standard deviation is 1.8 standard deviations away from the mean. So is that extreme? No. Find the height that has a z-score of 0.7. Okay, well, negative 0.7 equals the height that I'm looking for minus 69.5 over 2.5. And so if I multiply, I get, let's see, negative 0.7 times 2.5 gives me negative 1.75. So the distance, the deviation, is going to be negative 1.75. And so if I add 69 to both sides, I get 71 point. If I add, okay, let's see now. See, if I take negative 1.75 and add 69 to both sides, I get 67. So x equals 67.75 inches. Okay, compare data values from different data sets. So the standard deviation is a standardized way of describing a data point. Compare data values from different data sets. Okay, so find the z-score of each girl's time relative to her team. So she's on a different, they're not on the same team. Which girl has the fastest time relative to her teammates? All right, so let's go ahead and find the z-scores. So z z-scores. So for Angie, it's going to be 26.2 minus 27.2 over 0.8. So that's going to equal 1 over negative 1 over 0.8, which is, let's just see, negative 1 divided by 0.8. That gives me negative 1.25. So that's how many. So about 1 1/4 standard deviations below the mean. And then the other one, Beth, is going to be, Beth is 27.3 minus the mean over 1.4 over the standard deviation. And that equals negative 2. And so as it turns out, Angie is closer to the average for her team than Beth is. Beth is 2 standard deviations below the mean of her team. So which girl has the fastest time relative to her teammates? The answer to that is Angie. Angie is a little bit faster relative to her team. Okay, the following 2 rules give us a more precise idea of how far the data are spread from the mean based on the standard deviation. So, and then this is called Chebyshev's rule, is for any data set. So at least 75% of data is within 2 standard deviations of the mean. At least 89% of the data is within 3 standard deviations of the mean, and at least 95% of the data is within 4.5 standard deviations of the mean. Now this, again, that's Chebyshev's rule, 75, 80, 89, 95. But the so-called empirical rule, also known as the 68, 95, 99 rule, is only for data that is bell-shaped and has what's called a normal distribution. And so it says approximately 68% of the data is within 1 standard deviation of the mean. 95% of the data is within 2 standard deviations of the mean, and 99% are within 1 standard deviation of the mean. All right, so these are good to know. Just one more thing. The formula for population standard deviation is this right here. So notice it's a little bit different. Compare this to the other formula for standard deviation, which is x minus x bar squared over n minus 1. So no minus 1. Okay, so we won't use these formulas in practice, but it would be a good idea to get a feel for how to approximate the average distance between the data values from the mean, and to recognize that the formula for sample deviation and population deviation differ. Okay, that's it. That's all we have for today. Everybody have a great day. Thanks. Good luck on your quiz and homework.